Good evening and welcome to this evening's program. I am Tom Prince, a Bowen Professor of Physics at Caltech and Director of the W.M. Keck Institute for Space Studies, your host for this evening's event. Back in July, on the eve of the successful launch of the Mars 2020 mission and its Perseverance rover, Katie Stack-Morgan gave us an excellent tour of the landing site for Perseverance, Jezero Crater. Well, here we are 7 months later on the eve of the landing itself, and we are glad to have another great speaker for this evening. By my count, this will be the biggest audience we have ever had for a Keck Institute event. So since many of you are new to the Keck Institute, what is the Keck Institute for Space Studies? Well, in essence, we are a think tank for new ideas about future space exploration. We carry out our work jointly with the Caltech's Jet Propulsion Laboratory, and we endeavor to bring together best scientists and engineers from the US and around the world to participate in our studies. We undertake studies in planetary science, earth science, astronomy and astrophysics, and space engineering. Our goal is simple: to come up with new concepts that have the potential for significantly changing the future direction of space exploration. We have been consistently rated among the best US science and technology think tanks each year over the last 10 years. If you would like to learn more about the work of the Keck Institute, please visit our website and also maybe consider supporting our work, which includes programs such as the one we are hosting tonight. I'd like to also say that great talks like these have a lot of people working behind the scenes to make them possible. I'd like to especially thank this evening Kathleen Alva and Michelle Judd of the Keck Institute. And I'd also like to thank Leslie Maxfield, the Caltech video and audio wizard, for her work on the production of this and many other webinars. And lastly, we are very grateful to the Caltech Space Innovation Council for their continuing support of the Keck Institute. So turning to tonight's program, one of the goals of the Keck Institute is to help develop the next generation of space scientists and engineers. Among the activities of the Keck Institute is therefore what we call the Affiliates Program, a fabulous group of Caltech graduate students and postdocs with a passion for space science and engineering. The affiliates come together for pizza about once a month to hear a talk by a prominent space scientist or engineer. Tonight is just such a get-together. The affiliates have had their pizza already tonight, and they will now be your hosts for the rest of the evening. So I'd like to call on one of the leads of the affiliates group, Mike O'Connell, a Caltech graduate student in aerospace engineering. There he is. His research is at the intersection of engineering, control design, and machine learning to understand how to apply safety analysis of classical techniques to modern computing methods. And also in a lighter vein, his new hobby during the COVID period is brewing beer. So since this is an affiliates event, Mike will be introducing the speaker and also directing the question and answer period afterwards, and he'll be your host for the rest of the evening. Thanks for joining the Keck Institute affiliates for this talk, and enjoy the evening. Mike, take it away.
Yeah, thanks, Tom. Welcome, everyone, and thank you for tuning in and joining with us tonight to gear up for the Mars landing tomorrow. I don't think there's a better person to tell us about the thrill and terror of landing on Mars than our speaker tonight, Rob Manning. So Rob has been working on Mars spacecraft at JPL since the early 1980s. Just after he graduated from Caltech. He spent the first decade of his career working on avionics, software, and guidance, navigation, and control systems. Then in the early 90s, he became the chief engineer for the Mars Pathfinder, and he was the entry, descent, and landing, or EDL, team lead. This work really struck a chord with Rob, as EDL requires pulling together multiple disciplines and talented engineers to solve a really difficult problem, as we'll learn more about tonight. Since his time as chief engineer for the Mars Pathfinder mission, Rob has had a hand in nearly every US Mars mission in the last 20 years. He's received numerous awards from NASA and other professional organizations. One of those that really stood out to me was being included as one of the 100 people who made a difference in civil, commercial, and military space, named by Space News magazine. But that was in 2004. So now, that was over 15 years ago. He's worked on so many more missions and only continued to push the frontiers of space exploration. Possibly like many people, Rob's passion for space started when he was young, growing up reading National Geographic magazines, Time Life books on space exploration. And there's even going to now be a National Geographic special on this, I think this weekend. When Rob is not pushing, the boundaries of space exploration at JPL, he does other things like play jazz trumpet, paints, and skis, and he spends time with his wife and daughter. So to help us all learn about the thrill and terror happening tomorrow on Mars, please help me welcome Dr. Rob Manning.
Oh, Mike, thank you. But I'm not a doctor. I'm just Rob. But thank you very much. I really appreciate it. This is what a great privilege is to be here with all of you. And I know a lot of my friends are watching me. Friends who know EDL almost as well as I do are going to be watching here tonight. So I have to be careful what I say. This is a great thrill. So thank you. And I love sharing this stuff because, this is pretty cool. This is fun stuff. We talk about thrill and terror. People have talked to me before. Rob, this isn't terror. This is just, anxiety. Well, I have to admit, I guess I get anxious. What can I say? I've had a lot of wonderful experiences, and so I tell people, this is not, what you see is this looks like happiness, but it's not happiness. It's great relief. And hopefully tomorrow we'll have more great relief because these efforts to do this require a huge team of people, thousands of people, and the team at JPL and across NASA has done an amazing job, and I'm so proud of them. They're a really great group. And but I'm going to let you know how it started for me. I grew up in the 60s, and my view of space, my expectation was that by the 80s, we'd be flying people to land on Mars, just as Wernher von Braun and others and Chesley Bonestell argued in magazines like Collier's magazine with these wonderful paintings of. No, this is a really cool one. This is based on a 1950s design by von Braun, where he envisioned that we would be able to land a massive glider on Mars on skids. He thought the atmosphere was thicker than it really turns out to be. And can you imagine? So if this thing had really landed on Mars, it'd probably be landing roughly, 800, 900, maybe 1,000 miles an hour on skids on unprepared surfaces. I don't think the outcome would be that pretty. But anyway, I didn't know that when I was young, and I assumed that all this stuff would be easy. Well, the real truth of the matter is that we've had landing on Mars has been a real challenge, and we've had a lot of missions that worked. A lot of them have failed. We, being the human species, and we've had a nice run of successes lately in the United States. We're one single failure away from the simplest little thing going wrong. And I can tell you, there's an enormous amount of effort to make sure that we didn't miss that one thing out of thousands. And I'll talk more about that as we go, but it's been an interesting ride, and look at the diversity of stuff that's been sent to Mars. Look how different they all look. Yeah. It's like it makes you wonder whether or not we know what we're doing. So Mars has been splattered with human debris. Some of it real stuff that worked, some of it not so worked, some of it sort of worked. But Mars is probably feeling a little inundated by now, and there's more coming. Mars is coming tomorrow, and there's a Chinese lander coming in a month or two. So here's the timeline. You can see we've had the story started with the Mars 3, which is a USSR mission, which apparently lasted for a few seconds on the surface of Mars before dying. But the real first missions was Viking, and then there's a huge gap, a 20-year hiatus after we realized that there was nothing alive on Mars, no little green men, no plants, no water flowing, as many scientists already suspected. And we got a chance to do Pathfinder, and then a few years later, after some interesting failures I'll talk about, Spirit and Opportunity, Phoenix, Curiosity and Insight, and there will be more coming. So, including this one. So entry, descent, landing. That's what EDL we call it EDL. We've been calling it EDL for a while. So it kind of rolls off the tongue. And it's sort of, I look at, well, what could go wrong? Well, you know as well as I do, there's a lot can go wrong. But before we get to EDL, the EDL actually starts well before we even get to Mars. I think a lot of people want to know, don't understand this whole business of why can't we go to Mars anytime? Why is there a fleet of Mars spacecraft leaving now and arriving at Mars now? Why wasn't there one last year? Well, let me show you. So here, this is a simplified schematic of our solar system. There's the sun, there's Earth, and there's Mars. Earth is in the blue orbit. Mars is in the appropriately orange orbit. And I show as Earth goes around, what we do is don't let me tell you, you can go to Mars orbit anytime you like, but Mars may not be there when you get there. That's a key detail. So imagine you've launched your vehicle up, and it goes in this big looping elliptical orbit. Starts off fast as it goes past closest part of the sun. As it goes further away up to the top, it slows down, then comes back to the ground in a big loop. Well, the real key for landing, of course, is you would like Mars to be there when you get there. So what you do is you time it so that you time your departure so that Mars will be there when you get there. Mars comes around the bend. And then the fascinating thing about this, and I always love sharing this with people, is that because we're in an elliptical orbit, we're slow at that top part, but Mars is kind of cruising around in its big circular orbit. Mars actually comes around and hits us from behind. And so we have to kind of leap around and take a look. So the reason we can't go at any time we like is because Mars is only in this configuration where we can launch and arrive there. Every Mars, roughly a little over a Mars, roughly a Mars year or so. So every 26 months, and the window of launch is only about 3 weeks long. You could really stretch it. You know, a lot of you'll see if you saw the actual orbit. Sometimes those ellipses are actually bigger, much bigger than the orange circle, which means you can get there pretty quick. But so I thought once you do get there, now the trick is a little bit something about entry. E is for entry, and I'll talk a little bit about that. So we have, so it's fun to think about. So there's a picture of Mars, and I show to scale. I put Mount Everest in there to scale, and that we define an entry point 128 kilometers above the surface. Nothing magic about that. It's kind of an arbitrary altitude. That is defined to be above where the atmosphere starts. So what we do is we overlay some trajectories on top of this. Is our entry. So entry's coming from the upper right there, and it comes in. So I show 3 trajectories in parallel. In this case, for this picture, I show 3 because often people say, well, we're trying to get the angle right. You're trying to get as much atmosphere as you can. So if you come in too steep, you'll come in and whack the ground. If you come in too shallow, you'll bounce off the atmosphere. But what I'm showing here is that oftentimes when we talk about the entry angle being off, it's not the angle being off, it's the position. The angle is really nothing more than where you hit the atmosphere. So in this case, this was a real problem for us on Mars Pathfinder in the 90s because Mars hadn't been, as I mentioned before, hadn't been explored for 20 years. And in that ensuing, since Viking, and so in the ensuing time, we basically kind of lost track exactly where Mars was. So on our way to Mars, we were trying to aim for Mars and do this direct entry thing, just like Perseverance is doing tomorrow. And so we were very concerned that we could be off. And so the uncertainty in our entry angle really corresponded to an uncertainty where Mars was. And Mars could have been off as far as 8 kilometers, which it doesn't sound like much, but that's quite a bit of difference, quite a bit of variation. And it leads to a large error downstream, because you can see there's the entry angle right there. See where the arrow is pointed, something around 11 to 12 degrees. And then as you get closer into the atmosphere, you eventually get thicker and thicker, and then you start really slowing down. Now it doesn't, because you're really going fast, between 12 and 13,000 miles an hour in that window here. It doesn't take very long. It only takes about a minute or so to get from the entry point down to the peak deceleration point down below. Because you're going so fast, then the brakes really hit you, and you know, our vehicle is slowing down somewhere between 8 and 14 Gs, slightly between the angle and a bunch of other things. It's still it's quite a neck breaking event. And if you were on board, you would make sure you'd be wearing a very lying pretty darn flat, because it could be very hard on your back. And then we would get to really close to the ground there. Look at that. When we get to that line I've shown just above the surface, that's about 9 kilometers above the surface. that's by the time you're there, you've gone from 13,000, you're still going 1,000 miles an hour, 1,000 miles an hour. And look how close to the ground you are. Holy smokes. You got to pull that parachute because otherwise you're going to hit it. And so, so that's about where we open the parachute right there. And you can see, though, just the variation of uncertainty of position leads to a large uncertainty of where your landing insert lips. Now, there's that, and that's the only one of two uncertainties. The other big uncertainty is even if you came in really right where that little circle is in the upper, on the right there at the top of the atmosphere, the atmosphere variation of the density itself is very large at Mars. It's much, it's significant, which means that sometimes, depending on the density, you could be way down track or up track. It means left or right on this picture, quite a bit, just due to variations in the density. So if you're just a ballistic, means you're unguided, just a rock like Pathfinder, Spirit, and Opportunity were, then you're going to have some uncertainty in where you're going to land. Now, we could do, which is what we're going to do tomorrow, and what we did on Curiosity, and that is instead of flying this straight line this way, we flew it. We're coming tomorrow. We're coming a little bit differently. We're coming in steeper, and what we're doing is we're coming in, diving into the atmosphere, and then we're pulling up. Imagine an aircraft with lift. As you get closer to the bottom, you pull up. I'll show another picture about a lift a little bit later. But then you actually fly remarkably horizontal. In fact, you even gain some altitude before you ultimately open your parachute. So then you can see, so I've just annotated this picture here. So the result is you end up with a much smaller uncertainty ellipse of where you're landing. And so a lot of our challenges on Mars have to do with the fact that density of Mars atmosphere is only 1% of Earth. It's very, very small. It's like trying to land the space shuttle at 130,000 feet. You're still doing entry at 130,000 feet with the space shuttle. So it's really hard to slow down when your air is that thin. There's something else about Mars that you should know, and it's a lot like Earth. So I don't know if you've heard of something called the hypsometric curve. I love that word. It's called bimodal, which means it's got two big bumps. And those bumps, what those represent. So what this is that elevation, zero elevation in the middle of it means that's sea level. Everything to the right of that zero is above sea level. Everything to the left is below sea level. And what you show under those curves is the fraction of the Earth's surface that's in that roughly that range of elevations. Look how much of our surface is underwater. Well, that's not a surprise. 2/3 of our planet is underwater. And remarkably, even that big peak, remarkably, most of that is places like Nebraska, which is not very high up. So only a little fraction of Earth's surface is actually well above sea level. Well, Mars is the same way. It's shaped differently. In fact, it's got two humps, just like Earth does. And specifically, it's almost like there's an ocean on the left. You can see the big bump where there's something low. And on the right, mountainous regions, but unlike Earth, with the spike is near sea level, there's a big bump right there around 1.5 to 2 kilometers up, where a large fraction of Mars is. Now, the trouble with that, so let me show you where we've landed historically. We've landed, the highest mission we've landed was as Opportunity. It was about -1 kilometer, 1 point something kilometers. Everything else has been to the left of that. In other words, way below sea level. So we said, well, so you might say, well, Rob, why don't you just go higher? Well, it's that whole problem I was just talking about. You got to stop above the ground. Key detail. So we have this. So the problem, the ancient highlands on the right have a lot less air because they're sticking up into that very thin atmosphere. The northern lowlands, there's some air there. In fact, there's a lot more. The lower you go, the more air it is. Just like on this planet, the atmosphere is exponential. So that means you get more atmosphere quicker the lower you go. And you can sort of imagine this. So here's a full globe of Mars. And then, so imagine if you had a lander that can land as high as 2.5 kilometers. Well, that would rule out all the area in black. Well, that's not too bad. You miss out Olympus Mons, you'll miss out some highlands there. But the good news, by the way, we learned water flows downhill. And if you're looking for ancient life, water, and looking for where water once was, you can go downhill, which is actually a very relieving thing. But if you're trying to get, if your vehicle can only go say -2 kilometers, like Curiosity, Perseverance, look how much of Mars that you can't get to. Mars is a tough place. It's almost like if we're going to explore Mars, we're going to have to drive to these blue areas and I mean, land in the blue areas and drive to the highlands if you want to get there. It's going to be tough to land there if we're using atmosphere as our primary mechanism and parachutes and things like that. There's other methods. You could also use more fuel and do something supersonic reactor propulsion. That's much harder. Well, this all started with the Viking projects in the 1970s. And what's cool about the Vikings from an entry, descent, landing perspective, and by these missions were very successful. They did not discover life, but they did see interesting hints of odd things in the surface, odd chemical reactions. But the cool thing from an engineer's perspective is that these very smart people who were our inspiration early in the 1990s, and they were still alive back then. They no longer are, who gave us that not just inspiration, but actual technical advice and knowledge that allows us to use their supersonic parachutes and the hypersonic entry space capsule and the thermal protection system that we use for mission after mission, as well as the idea of the propulsive throttled engines that very much like the Apollo landers used for landing humans on Mars. And you can see, so we adopted those. So Vikings on the left, on all these pictures, these are all the space capsules with the heat shields on the left and all of them. And all the heat shields look identical, don't they? They're all the same angle and the same geometry. Well, that's no coincidence. Is Tabek, this guy here in the glasses in the middle there, told us to do that. And we had some good data to say, well, that was a good idea. And so the only thing that remind us to do is make sure you make that heat shield as big as you possibly can relative to the mass. And to make sure that the mass to heat shield area isn't too high. What we've been doing with our larger vehicles like Curiosity and Perseverance is that even though we've made a bigger aeroshell, look how big they are compared to a person. It's still getting heavier and heavier and denser. And so that ratio of mass to heat shield area is getting higher and higher, which means you have to do these tricks like aim deep into the atmosphere, cut it high, and then pull up like a pilot. In a very dramatic entry. So anyway, so 20 years later, we took their ideas. Unfortunately, in Mars Pathfinder in the early 60s, we didn't have the wherewithal, the money, or the time, or the technology to reinvent the throttled engine. In the 20-year interval, that throttled engine had really all but vanished as a capability. So, we could, no one would need them. I mean, you don't land on the moon of Mars very often. That's the only application that was around for this thing. So nobody was doing it. So all the people who knew how to do it, the companies who made it, all disappeared. So we said, well, how about this? Well, just some silly solid rocket motors, attach it to the back shell of the space capsule, lower our vehicle down in airbags, and fire these rockets that stop us just above the ground, some meters above the ground, and then we'll bounce on the surface. And that's exactly what we did in the 1990s with Pathfinder and delivering a little Sojourner to the surface of Mars, and a fun little mission for lasting 3 months. In the process, we learned all about soft goods and fabric, and ropes. I didn't know I would have to learn about ropes and fabric and denier and other attributes of fabric, but we had to learn all those things. Meanwhile, after Pathfinder, there was still the idea, well, we can use the throttle engines, but the throttle engines technology wasn't around. So a group of people led out at Lockheed Martin and some of their colleagues at JPL developed this idea of using existing thrusters, they're just on-off thrusters, putting 12 small thrusters together and firing them on and off in a pulse mode, like a bunch of little machine guns. So imagine 12 machine guns strapped to the bottom of your chair. If you fire them off and on, tick, 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 fast enough, you can land this. You can land your chair, and it's about as dramatic too, because the ride is pretty darn rough. But that actually worked, and that's how Mars Polar Lander worked. Was intended to work. How Phoenix worked, how InSight worked, and they all succeed. The Phoenix and InSight all succeeded with that technique, and it worked very well. However, the bad news for Mars Polar Lander in late 1999 is that after we had a long story about Mars Climate Orbiter just a couple months earlier, this vehicle in interest, we saved some money by not having a communication system on during entry, descent, landing, unlike what we're doing tomorrow, and it came in quiet. And we weren't watching when it landed, but when it finally landed, we were hoping to get a signal back, but we never did. And subsequently, a team using the high-res camera on the Mars Reconnaissance Orbiter has taken something like 50 to 60 gigabytes worth no, I'm sorry, terabytes. I'm mistaken. Terabytes of JP2 files of that area, and we've seen no sign of it anywhere. We think we know what may have happened to it. I suspect, as some of my colleagues suspect, that we didn't make it through the entry phase, but even though the official cause is that it failed on landing, but we don't see any sign of it on the surface. It doesn't mean it's not there. Could be covered up in dust, but I suspect that's not what happened. Well, so after that failure, we had to come up with something in a hurry. So because, as you know, you can only launch every 26 months, and the next opportunity was to launch a vehicle just like it. We didn't know what to do with that, why it failed, so we couldn't launch that one. So a couple of colleagues and I got together, and we proposed the idea of modifying Mars Pathfinder. Pathfinder's on the left. See that little white box, the JPL letters and the U.S. flag and the missing NASA meatball. Sorry about that. Imagine if you just got rid of that white box and replaced it with rather than a tetrahedral shaped box, replace it with a tetrahedral shaped rover, and get rid of a little Sojourner and add some little bat wing ramps to get this rover off. And then you can just take the same design and land it. And that's exactly what we did with Spirit and Opportunity. Actually, 3 years and a month from the date that we proposed it, from about a 24-page PowerPoint package, as Mark Adler, who's listening, will remember. I think it's 24-page. Anyway, so we pulled it off. We landed those things. Now, we used the same idea, this rockets, but we had all dickens of a time. One of the trouble with the same tetrahedral-shaped lander with the same airbags as Pathfinder, it turns out this little rover was denser and it was heavier than Pathfinder. So we had to stuff more stuff in there. So it turns out when we started testing our airbags, they're all being torn to shreds. So we had to do something. We said, what are we going to do? We need to find some way to slow down, control the velocity better. Is there some way we control those rockets better? And it's not the rocket's fault. It's the fact that the wind pushes that back shell around, it produces all these different angles. Plus the parachute itself can move across the ground at a good clip if there's a horizontal wind. And so we came to the idea, so what if we added a small camera to the radar bracket, and we added 3 small rocket motors and fired them just when we fired the big rockets, and to adjust the angle to make up for that velocity. And that's exactly what happened. A little video you were seeing there on the right, if you can make it out, you can notice that's actually Spirit's landing day. It's a reconstruction. That's what we figured out, exactly what happened. And we pushed that parachute was pulling us to the right. We had to do something. We had to push that back shell over by firing 2 rockets and push it on over and get it to slow down. And that's exactly what happened on January 3rd, 2004. So D is for descent. So just point out though, this what's interesting is so that's the first time we'd use a camera for using kind of image kind of processing on board with the camera. Still just using that, we use that camera strictly to get velocimetry, basically measure horizontal velocity to help, so we can use that information to help cancel the effects of wind. So we did that. So one of our problems has always been this classic thing called a parachute, which this is how it's supposed to. Oh shoot, that's not the one I wanted to show. That one all ripped up. Well, of course it's ripped up. These are parachute tests we performed some years ago in the world's largest wind tunnel. It's called the NFAC. It's 100 by 80 by 100 cross section up at NASA Ames Research Center. It's currently run by I believe the Army, but it's an incredible facility. But we've used it for testing parachutes and very successfully for many years. Oh, shoot, this isn't supposed to happen. And we basically use it because this is subsonic test, but we're using it for strength testing of these parachutes to try to reproduce the environment. And so we said, we need to do this right. Let's take some bigger parachutes. We want to push the envelope. And these are 2 tests that were formed a year apart in Hawaii over the Pacific. And what you see there is a drag device. Ignore that. Here's the parachute open up. Oh, ow. Oh, shoot. Oh, that wasn't supposed to happen. Well, so what did we learn? Well, we learned that parachutes are hard to get right, and it's easy to underestimate the forces that are on a parachute when it opens up supersonically. And so since that time, we redesigned parachutes, we built them, we tested them, and here's what it's supposed to look like, and that's about the speed of inflation. You remember, that's a 21.5 meter parachute you just saw open up there. It's really big. A person's really tiny. Look how fast this thing opened up. Anyway, so parachutes have been one of our bugaboos, and it's probably the one, I still think it's among the most risky aspects of entry, descent, landing, because, you know, on Earth, we never open up parachutes going, you know, approaching 1,000 miles an hour. That's crazy. So L is for landing. You've seen a lot of diversity in the landing. You see airbags, the Viking style Phoenix and Insight landers, and of course this new funny business thing called Skycrane thing that showed up with Curiosity. What's that all about? What were we thinking? And so, so it really started when in the early 2000s, even before Mars Polar Lander arrived. We were wondering how we're going to get large rovers to the surface. We knew about how to get Sojourner there, and we had some ideas how to get something like the size of a small golf cart there, or a large coffee table, as Spirit and Opportunity are there. And of course, the question is, how do you get something as big as this, a real laboratory to Mars, or a thing that's going to collect samples like Perseverance is going to do, starting hopefully this next week, and or even bigger. You know, you can imagine something bigger, maybe not quite that big, but they're big. You can see the mass grows as each iteration of these missions, and mass and volume. So the question is, how do you land this? And we can imagine all sorts of techniques, you know, stork delivery. You can imagine. So what happened was in 2000, just even before Spirit and Opportunity were invented or conceived, we were playing with some groups, a small group of us were working on various enumerated ways to think about how to land, how to do entry, descent, landing in its totality. And we looked at all these different options in about January in 2000, and we came up with some ideas that were, you know, just modifications of existing design. There's one with outriggers. What about you could imagine you could land your rover underneath a lander with really long legs and just kind of like a land and just have it lowered to the ground once it's landed like this. You can even use big airbags. You can imagine big airbags with a more liquid propulsion system is one of the things we conceived, and to try to land a big rover there. And so that by controlling the velocity, you wouldn't have to bounce as much. You might not even need to put airbags all the way around it. Or you could do the kinds of things that the Soyuz capsule does in the desert just before it lands. Some solid rocket motors fire, stopping the vehicle just before it hits the ground. Another possibility is just to use a pallet lander, which is a very flexible lander that could adapt itself to the surface. And we worked on that for a while. There's another wild idea we have is, what if we just use a propulsive descent stage helicopter thing to land it on its wheels? Nah, that's just crazy. And so this is actually a view graph from that period that we were playing around with it. And that interesting that those velocities down the lower right are pretty much the velocities we actually end up flying. Well, after some time, around July 2002, it took us a while on Pathfinder, I'm sorry, Spirit and Opportunity with these struggle with these little rockets I told you about earlier. We said, well, we really need some way to control the velocity really well. Like, and if we could lower it down on a rope, we could be very gentle, and we wouldn't have to have airbags or a lander at all. Stop screen, and I'm going to give you a little demonstration. So one of the biggest challenges we had, I think, can you guys all see me okay? So this, hey, I'm careful not to hurt myself. This is, very dangerous. So one of the things we thought was, well, you know what, this system is really a pendulum. And we said to ourselves early on, it's really hard to land something that's on a pendulum. So especially on its wheels, because if you have any angle like this, you'll damage the wheels, and wheels would be a terrible landing gear. But then on Spirit and Opportunity, we were working on those little rockets, and we started developing the algorithm. People like Miguel San Martin would say, "Hey, Rob, we can control this thing." And one of the things that we discovered is that the algorithm for damping the motion is very simple, because this is not a pendulum. This is the descent stage is up here. It's very agile. It could make little turns back and forth, especially, as Miguel pointed out, if you put it in the middle of the center of mass of the descent stage. So one of the things we do is that you can move like your fingertips. You can move it around like this. So imagine you're swinging like this. How long do you suppose it would take to damp out that motion? Ready? Say, 1, 2, 3, stop. 1, 2, 3, stop. Stop. It's really easy. You can do it with your eyes closed. So we realized that that was actually a really easy problem to solve. The algorithm was very easy. So once we realized this, and we put it to use and figured out how to lower the rover down, we actually had a design, and Adam Stelzer and others dubbed this design Skycrane, the Skycrane maneuver to lower from a dense descent stage. And there we had it. It was our design. We did have some other problems along the way, but it worked with a heat shield falling apart. We had to get rid of our Viking technology. We had to go to a phenolic ablator as opposed to the TPS we developed on Viking, thermal protection system. But let me talk to you quickly about Perseverance versus EDL. So what's new about tomorrow? So we're landing in Jezero Crater. It's 45 kilometers across, about 28 miles. What we're aiming for in the upper left of that picture, and I'll show you. But first, I'm going to show you, remember these ellipses, the big ellipse? The ellipse we had for like Pathfinder or Spirit and Opportunity were it was the area of Rhode Island. When we added guidance, we were able to, on Curiosity, we were able to really reduce that quite a bit to an area the size of much smaller, something the size of the Washington Beltway, or Greater Washington DC. And but now we've added another trick, because we're coming in horizontal with a parachute. If you time the parachute inflation, we can stop the vehicle more carefully over the landing site simply by timing when we inflated the parachute, because we're coming in from the left horizontally, boom, open the parachute when we're over that landing ellipse, and we'll fall straight. The parachute then straightens out, and we start descending straight down. So that's that same ellipse is zooming in there. It gives a sense of scale against Manhattan. So our new landing area is about the size of Manhattan, about an 8.5 by 9 kilometers ellipse, more of a circle this time. They're mostly driven by what the winds will do to us. And if it's not a windy day, we're going to come pretty close near the middle of that thing. But, look at that. There are hazards here. There are all hazards all over that landing ellipse. So one of the things that we needed to do is, how are we going to find it? So scientists want to go this place because there's some great mineralogy here. This is an ancient water outflow. Clearly it was water, right? You can see the water there's a river, right? And our plan is to drive up toward that river and uphill to the left. So we want to get as close as that as possible. So the real trick here is figuring out how to avoid obstacles, even though you're going to land anywhere in that. You don't know where in that red or orange circle you're going to land on. You need to be able to somehow find a safe spot in that, for any place in that circle. So we're on Thursday at about 12:36, 10 minutes before entering the atmosphere. The cruise stage is going to separate, like we talked about. We'll get rid of it. We'll get rid of, throw away some extra mass on the vehicle, on the bottom half of the vehicle. That will cause the vehicle to tip a little bit. So as it flies through the atmosphere almost horizontally, it'll get lift. Just like when you stick your hand out the window when you're driving your car at an angle, your hand will be lifted up. This same thing here. And we can use that lift by steering that vehicle, by rolling it back and forth to glide ourselves with big S-turns to our destination, to control how well we're going to target test spot. So not just left and right, but up and down. But the tighter the S-turns, the less distance you need to travel. You're going to travel even if you're going too fast. Next, so then we open a 21 meter diameter parachute that's launched on a mortar cannon. A mortar cannon. Check out that. That's a real mortar. This is what it actually looks like if you were there. You'd see a big flash of flame. And then some seconds later, we'll open at about, we're still going 200 miles an hour. We open up, the heat shield falls away. We're for the first time in history, we're going to use a camera, not just to take pictures of velocity, but actually to figure out the rover on its own is going to figure out where it is. It's got onboard images of the site that's taken from Earth. We gave it to the rover, and it's going to take images from its camera and compare its images with the onboard images. And with this two-dimensional image correlation, we'll be able to deduce its location. Well, from that, we can also use another map effectively to look up to see whether there's a hazard there or not. And if it turns out vehicles look, it's going to be a hazard, the rover makes a plan to land someplace else, the next safest place. And that's this technique we called terrain relative navigation. And we'll do a up to 600 meter divert maneuver to avoid obstacles and find a safe place. So hopefully that'll be tried out tomorrow too. And so the engines were to life about a mile up, and then and we use a radar just like Curiosity did on the way down. and then slows down to about 2.5 miles an hour, and about when it's about 70 feet up, and gently lowers the rover down. The wheels deploy, and at the same time, we're taking images. Now we have a camera looking up at the parachute when it inflates. We have a camera on the descent stage looking down as the rover is deployed. We have a camera looking up at the descent stage. We have another camera looking down from the rover. It's just amazing. We're going to have more video, not tomorrow necessarily, but in the coming days, and maybe some snippets tomorrow of EDL than we've ever had before. And hopefully we'll learn something. And so once we land, it'll come to a stop, and it will we'll cut the cables, and the descent stage will fly away and crash land about 600 meters away. So a lot of stuff has to work. 3 sets of batteries, multiple computers. I won't want 79 post-explosive devices. I say it all the time. Mortar cannon, thermal tiles, 16 rocket motors. Boy, it's like a partridge in a pear tree. It's amazing how much stuff is in there, and it all has to work. There's very little in the way of redundancy for many of these devices and mechanisms in particular. So we're going to be listening to tomorrow the New Space Network, as well as Madrid, Spain, and we're getting signals directly from the vehicle up until just before cruise stage separation, in which case we'll get, rather than getting ones and zeros, we'll get tones. And so we get tones most of the way in from just from an X-band signal, which is not very much. It's basically a bright flashlight. But the cool thing is that you can see that line coming on horizontally there. That's Mars 2020, that's Perseverance. Turns out MAVEN and Mars Reconnaissance Orbiter are strategically placed so that they're flying overhead and in view. And what's great about that is that Mars 2020 will be able to send, just before entry, we'll start sending ones and zeros to Mars Reconnaissance Orbiter, which then relay those ones and zeros all the way to the JPL, via the Deep Space Network. And we'll be able to hear what's going on and listen in to what the rover thinks it's doing, and what it senses. And so that's going to be very cool. And so with luck, we'll be doing this and not just in a few months' times. We'll be doing drilling and into coring rock. We'll also be doing this. Okay, so here's an animation of everything I just explained here. There's the vehicle coming at us there. The cruise stage is separated, and it's separated in such a way that it stays away from us and it burns up parallel with us. We fly a little bit away from it as we enter. And those are reaction control jets, which help do those roll maneuvers I was telling you about, as it enters the atmosphere and slows down from about 12,500 miles an hour to about 1,000 miles an hour when the parachute opens up. And there it is right there with the heat shield's about to come off. Well, actually, the parachute has to open up first. And now we're just finishing that up. Now we align the vehicle the right direction, we're heading alignment. The parachute opens up just like you saw in the other video. And about 30 seconds later, the heat shield is popped out and we'll get our first view. The rover will get its first view of Mars. Meanwhile, we got a vehicle, a Mars Reconnaissance Orbiter is not only relaying data, it's also going to take a snapshot from orbit, like we tried with MSL and with Phoenix. And we tried it again with InSight, but we missed. But hopefully we'll get this camera. And then we do this divert maneuver. So if there's an obstacle in the way, that descent stage moves out of the way, and moves the vehicle. We call this a propulsive descent configuration, the PDV. And we just slow down, and eventually go straight down once we get over our safe landing zone, and lower the rover down straight. And about 70 feet above the ground or so, we lower the rover down. There's the helicopter nested below in its protective shell. And the 3 cables are cut, as well as electrical cable, and off the descent stage goes. And we're on Mars. Okay, that is our story in a nutshell. And hopefully, the great thing, we didn't have to climb off a lander. We didn't have to, there were no ramps involved. We were directly on the surface. So this landing technique of using the Skycrane maneuver really is a very effective way to get a rover of this size and shape and configuration on the surface of Mars. So I'm going to stop right there and stop sharing. So thank you very much. I spoke fast. I hope it was not too fast.
Yeah, thanks, Rob, for taking us through the thrill and terror of landing on Mars. We have a ton of questions that were submitted, so I'm going to get right to it. So the first question is, how do you define sea level on Mars? And this one was a popular question.
So it turns out the Mars Global Surveyor carried an instrument called the MOLA instrument, the Mars Orbiter Laser Altimeter. And what they did was they very carefully with 100-meter resolution, they mapped the whole globe elevation-wise, and they arbitrarily selected sort of what they thought was the middle ground in terms of elevation, subtracting the measured elevation with an ellipsoid that defined the shape, the mean shape of Mars. And so that shape variation became the definition of elevation. And that's been the standard that we've used ever since. And I think it's sort of become the de facto standard for Mars for everybody, because all the maps and everything are based on the MOLA map, based on the MOLA instrument.
Cool. So the next question is from Rafael Avila from ECMSG in Los Angeles. And the question is, do you think it might be possible to live on Mars? Will the rover be able to gather evidence to see if we might be able to?
Well, in fact, yes. As a matter of fact, one of its instruments is the MOXIE instrument. And its mission is to extract atmosphere from Mars, which is, even though it's only 1% of Earth's, still got quite a lot of it. It's carbon dioxide, CO2, and it's possible to pull apart the carbon from the oxygen and create oxygen from that, which is a very useful thing for surviving on Earth, surviving on Mars, as you can imagine. Because once you have oxygen, it's possible also to grab hydrogen from other sources and put it together to create water. And so you can use oxygen, you can create oxidizer fuel for your fuel, and there's a lot of things you can do. So that's one key part about the possibility of eventual habitation that this project will endeavor to solve. But its primary objective, and I didn't spend a lot of time talking about, is the main objective of this mission is not EDL, even though I make it sound like it. It's to go to Mars to study the possibility for ancient life, and particularly not just to do in situ exploration of Mars with these fabulous new instruments on the end of its robotic arm, but also going to collect core samples and put them in sterile, ultra clean sample tubes that are sealed up with core samples or soil samples or even atmosphere samples. And we'll leave them on Mars in a pristine way. So a more dirty rover can come along in a future mission called sample return, grab those tubes, put them in a rocket and send them into space. And so this is the step one of the sample return mega story that we hope to have happen. Because ultimately, even though we send these fabulous instruments to Mars, the equipment we have on Earth, the ability to analyze things with incredible precision and to double check using ultimate methods is so much more powerful here on this planet. Scientists on this planet are just pining to have real samples from Mars, pristine samples that we know where they came from, the conditions in which they were sampled in collection, what was the context that they were created in, by looking at the surroundings, environment.
Yeah, that will be great to have back here on Earth one day. So the next question is from Ruby Ann Vallejo, who's a student at Norma Combs Elementary School. And she asked, how do you program a rover to go to Mars? And what kinds of coding do you use to control it?
Well, if some of you folks on FIRST Robotics, you guys know how to program something. You just write software and you put it inside the computer and you hit go. And the trick is, it makes it sound easy, but you just have a lot of people work very hard working with these sensors and testing all the time. We've tested the amount of testing required to pull this together is unbelievable, really. But it's no different than trying to control writing software for your own personal robot, your FIRST Robotics experience with the various robots that you can buy yourself. And so it's just a lot more elaborate with far many more lines of software.
And many more hands working on it too.
And many more hands, hundreds and hundreds, if not thousands.
So the next question is, as a spacecraft is approaching the landing site, do you need to check the weather conditions before landing on Mars?
In fact, we did. We had our weather. We have weather reports. We collect weather data from instruments on our orbiters, and particularly Mars Reconnaissance Orbiter. We look at we get thermal. We look at grazing angles through the atmosphere to get the temperature and the absorption of various colors of light to give us a sense of how the atmosphere is doing, whether there's dust accumulation in the atmosphere. We've got pictures that look down that can see clouds and dust build up. And so, yes, we do. In fact, we did this. It turns out at our landing site tomorrow, it's going to be pretty clear and cool. And so we're not too worried about that. The weather is great. Had there been a serious dust storm though, we would have adjusted and tuned up some of the software parameters that we can tell the spacecraft here how to do EDL tomorrow, but we wouldn't be worried because we've convinced ourselves that this design, especially with this guided system and the robust thermal protection system, is relatively impervious to dust. And because we're not solar powered on the surface, even if it was a solar ray rover killer, such as what happened with Poor Opportunity rover, where it got so dark and so dusty, it had virtually no electricity was going to a solar power. We have a separate plutonium powered source of energy, of perpetual electrical energy that can get us through even the darkest dust storms. So the good news is this system's really robust to that. And so but that wasn't always true. Some of our missions were not so robust to it, but this one certainly is.
The next question is, how long does a Mars rover last until it dies? Alluded to by the solar panels on Opportunity.
Well, so this one, since this doesn't have solar panels, it has this radiothermal isotope generator, electric generator. It produces only about a little over 100 watts of electricity. Doesn't sound like very much for such a big rover. I mean, you get 100 watt in the old days, before LED lights, we would get 100 watt light bulbs and just put it in in the middle of your room, and that would be one little light source. But it's enough to charge the battery, and that's what we use it for, to charge the battery. It can basically trickle charges the battery all day long. But that thing will last and last. Now it does degrade with time. Just like Curiosity has degraded with time. It landed, it was a little over 100 watts when it landed. And now it's somewhere south of 90 watts, I think, something like that now. It's getting worse and worse over time, but it's really slow. And what's more is that we know how to, if it gets, the weaker it gets, we just do less on a given day and just spread it out, the energy out. The good news, so that's the good news in terms of design life. On the other hand, things can break. And we have had our vehicles break, either through wear or issues with lubricant, or even design flaws that we didn't catch before we launched, which are very common. And so, and I just got to warn you tomorrow, and for all of us, is that we got to remember that we're only human beings. We're not, even with thousands and thousands of things to go right, even the best of us can make a mistake and miss something. And so, I hope we don't come away thinking that this is a slam dunk. It isn't a slam dunk. It's very hard. And the good news is we figure out over the years how to find ways around to keep things going, as we did with Spirit and Opportunity. Literally, when we designed Spirit and Opportunity, I swear we really didn't think it could make it through the winter. I thought maybe more than it was designed for 90 Mars days, but I was talking. I remember talking to Jake Matijevec, who was our system, the late Jake Matijevec, wonderful fellow, who said, Rob, I think we can get to 120 days, maybe if we're lucky. But we didn't count on something that showed up on Mars. It took us, we were able to squeak out longer than 120 days, but we had something that happened on Mars that was very unusual. It was in that we had dust cleaning events, this high-speed wind that essentially sandblasted the fine particles of dust that accumulated on the solar panels. But we can't count on that. InSight is on Mars right now. It's got dust accumulating on its solar panels, and there hasn't been a dust cleaning event. There's not, and by the way, we call them dust cleaning events. it's a secret way of saying little, Martian monkeys with Windex going cleaning out the top of your solar panels. No, it's wind, but we can't count on it. And so the great thing about this power supply that we have in this vehicle is that we can count on it, as long as it doesn't break and doesn't short out, or we don't have electrical failures or shorts or things go wrong, which could happen.
All right, so the next question is from Finnegan Keller, who's a high school student. How, if at all, does the climate of Mars affect the design of Perseverance's instruments?
Well, the climate plays a big role, particularly the changes from summer to winter. Mars has very large temperature swings in a single day, but they're very predictable. If you know the weather today, it's going to be pretty much the same tomorrow. But over the course of a season, though, it can get very, very cold. And even though we're not that far from the equator, it can get pretty warm in the summertime too on the surface. Now, the fascinating thing about Mars is that you can say it's getting really hot on the surface. It's room temperature on the surface. It's boiling. But at your nose or even higher up, it could be 40 degrees below zero, just a couple meters away from the surface. And so, but in the winter, it's even worse than that. So for instruments or other things that have to especially the ones that have to stick out in the breeze, they have to be designed to handle those temperature extremes over the whole annual cycle, because this vehicle's designed to last a Mars year or longer. So it's got to be able to handle a Mars winter, and by design from the beginning. That was not a requirement on Spirit and Opportunity because we were only going for 90 days in the summertime, even though we managed to hunker down and survive the winters, several winters for each of the rovers.
So the next question is, what happens to the vehicle that delivers the rover? So the Skycrane.
The descent stage. Oh, the poor descent stage. Someday we're going to put software on it. We're going to take it, fly it away, and then have it kind of try to land safely so it doesn't explode or anything. But this descent stage will, like Curiosity's, end up crashing into the ground. And so it does crash, unfortunately, because it's unfortunate because we put a lot of money and time and effort into it. And so it's kind of sad to see something that you just be very, very careful with your fingers and polish up so perfectly, crash in the ground. Same with the cruise stage, which melts on the way to the surface. So unfortunately, our technology is still pretty messy in that respect. And no, the good news, it's not that hard to clean up. If I was there at the pickup truck, I probably could get most of it in an afternoon. But it's still some days we'll come up with a descent stage that has a more graceful landing. Yeah, even if it's an ugly graceful, just as long as it doesn't explode. One
day there will be reusable descent stages on Mars.
Yes, and you can imagine you can put more fuel in it, and if you're lucky, you can fly it off somewhere else. Now it'd be really hard. You have to be really full of fuel in order to get it completely out of Mars and back into orbit again. But you can imagine that idea, yeah.
So our next question is, what kind of time delay is there between instrument observations made during observations during landing and the time it takes to get back to Earth? And does that complicate the landing sequence?
Well, I will answer the second part first. It doesn't, because everything about the landing sequence is pre-programmed in advance. In fact, we gave the command, the do EDL command, which is what we call it since Pathfinder days, last week, or late last week. So the rover, once it gets that command, it says, okay, I'm ready to land. And with that do EDL command, you tell it when landing going to happen and where we want it to go and everything. So it has all the information it needs to land. What we're doing now is updating that information, tweaking it a little bit. But if we don't tweak it anymore, if we don't talk to it anymore, the vehicle is on its own. There is no need for us to talk to it. And so when you see us all in the room tomorrow, or you'll see the team jumping up and down or staring at the consoles, what we're doing is we're monitoring different parts of it, because different parts of the rover to communicate have different parts to talk about. They have different things to talk about in different areas. So the team is able to monitor what's going on, but we're not involved in it at all. So that delay is not a problem at all. In fact, when we're leaping up and down, or when we say, "Oh, look at the cruise stage, we're entering the top of the atmosphere." Well, On Mars, it's actually already over because it happened 11 minutes earlier, because that's how long it took for the radio signals from both from our rover, as well as the one data that's been relayed from Mars Reconnaissance Orbiter to get back to Earth. So, but when you're operating a rover on Mars, that time delay is significant, but another delay is even more significant. It turns out our rovers, because we only have 100 watts electricity, we don't have enough energy to stay awake all the time. So what we do is, imagine if you were comfortable to be at home and you had a team down in the Antarctica, who's doing all this, do the scientific work for you. They would do all this work during the day. They would send you the results, and overnight, you and your team here in the comfort of your living room would figure out what you wanted that team to do tomorrow while they were sleeping, and you would come up with a whole script of what you want to do. And in the morning, the first thing you do, just before they wake up, just when they wake up, you send them a list of things to do. That's what our rovers get in the morning. When they wake up, they get a list of things to do. And sometimes that list goes a day. Sometimes that list may go for several days. But nevertheless, they wakes up as, okay, this is what they want me to do. Okay, let's get going. And the rover operates without us being involved at all for several hours before it gets sleepy or runs out of energy, and it shuts itself down and sleeps for another 10 hours, right? Or more like 16 hours until next morning, and it repeats the next day. But so in some sense, that the time delay due to the actual distance from Mars is not as important as the fact that we don't have enough energy to communicate and allow us to interact with it in a more dynamic way, like you do on a telephone. It's much more like email versus a telephone.
So that actually was our next question from Talua. So we will go on to the last question now. So this is from Ella at John Muir High School. What is the experience of mission control and the relief felt after a successful landing during the pandemic?
Well, it's great relief. I can see it feels like it looks. You imagine you've spent not 6 months, but you've spent maybe 4, 5, 6 years working on something that you've been trying to visualize and work out and argue with people with how to do it. And they said, no, I want to do this way. No, that doesn't make sense. We should do it this way. And then you would talk about different ways, and you finally get the design right. So, okay, let's try it out. Oh, it didn't work. We have to fix this. And you just on it I didn't look. Oh, look at this. We made a mistake here. We got to find that. Got to fix that. And you're doing that all the time. Constantly. Well, what if this doesn't work? If that doesn't work, we can do this. That's the kind of thing that people goes through their mind all the time. And you're basically thinking about all the ways that things not going to work. In fact, we spend far more time thinking about the way our machines aren't going to work than we do thinking about how they are going to work. Kind of weird, huh? But when the actual landing happens, you've been thinking about all these things that could go wrong, and all the things you thought through and all the designs. And now the information you're getting tells you it's over. It's all in the past. It all worked. But in your mind, you're still worrying about them. And you may still worry about them, like, oh, shoot, I didn't do that. I didn't set up that parameter. I was going to set up a week. Oh, shoot, I was going to do that. Well, it doesn't matter now, does it? It's all over with. So it's a very strange sense of feeling of, it's a bit traumatic. Even when it works, it can be a very bit traumatic. So it's a very, very strong emotional feelings, especially when you spent that much part of your life, and especially not just during the weekdays, but for many of these my team members, these folks worked weekend, not me, because I was the chief engineer of JPL and just watching this stuff. This team worked hours and hours, evenings, weekends, nights, days, leaving their 4 families behind, and just struggling to make this all work. It's been, it's hard. I know what that feels like. I've been there, but I tell you, it's hard, and it's hard on this team. And that's why seeing this thing come through tomorrow will mean so much to them. But also, if it goes well, it just reminds you just how much when people come together and they work hard toward a vision, and they work with honesty and integrity, and work hard and they have perseverance, they can make something happen. You can solve problems. It's possible for human beings to solve the problems, whether they're natural problems that we create for ourselves, like landing on Mars, or the problems that we created for our own planet that we have to solve as people. And I think this is a reminder that solutions are there if you work at it and you come together and you listen to each other and learn from each other and do it honestly and openly.
Yeah, well, thank you, Rob, so much for your time tonight. So I think we sent you a small gift. Hopefully that'll go with the relief that you're feeling with the landing finally approaching tomorrow.
Yeah, this just arrived. Thank you. This is the gift, right? Yeah, just double checking. What is this? I think I know what this is. Peanuts.
That's right.
So if people don't know, JPL isn't normally that superstitious, but we have this tradition going back since the 60s after a series of failures of Mars. I'll mention it tomorrow during the NASA TV thing of opening peanuts and sharing peanuts the night before, just before a big event, kind of for good luck, but also it's just a tradition. But it's a wonderful tradition. So I want to thank you. Oh my gosh, there's more. Not done yet.
More things still, yeah.
Oh my goodness, look at this. Now, this is important for all of us. A Mars bar. These are hard to find on Mars, I tell you. And they're actually almost as hard to find on this planet too. But thank you very much. This is fabulous. Oh, this one cracks me up. Can you see what this is? Loaded dice. And this is maybe more appropriate for airbag landers to have to roll. People wonder, how can you keep landing on the base pedal down? No, but this is how we deal with uncertainty. We try to stack the deck, load the dice in our favor, and that's exactly what we try to do. We do it without cheating, but we do definitely try to win, because it's not a precise game. We can't be positive that we've done it right. And there's residual risk in almost everything we do. I'd like to tell people that our designs are the least unsatisfactory designs we can come up with. And never the best. It's impossibly the best. This is also cool. Look at this. Oh, is this a playing card? Oh my gosh, look at that. Oh, this is really cool. Check these playing cards out. I've never seen these before. That's a big smiling rover. You probably can't tell, but there's a big smile in that rover.
Oh, we can tell. I think the cards might be one of a kind.
Is that right? Oh, this is priceless. Thank you. Oh, I love this. Oh, this is so great. Thank you so much. Wow, that is amazing. Thank you so much. I didn't deserve that, but I really appreciate it. And it's so fun to share all this stuff with so many people. And of course, I'll be getting emails tomorrow with all the things. Rob, you got this wrong. That's not the right number. Yeah, sorry.
Yep. You'll have bigger things to be excited about tomorrow.
So yeah, I count on my colleagues to correct my mistakes and vice versa. And that's how we succeed, by the way. We catch each other and look out for each other.
Yeah. Well, thank you again, Rob, so much for your time. I think we're a little bit over, but I think that's okay because we're all excited for tomorrow. Lucky peanut.
I am too. Well, thank you very much, Mike, and thank you to the KISS team for inviting me to come and speak with all of you today.
Yeah. So I just want to remind everyone in the audience, if they could just please take the time to fill out the survey when you leave the lecture, and then also a quick announcement, which is that we hope you attend our next KISS webinar on March 17th. That's with Dr. Sarah Spangolo, discussing Swarm, a new paradigm for communication satellites. And of course, we also ask that you attend some of the other Mars landing events tomorrow. And I think the one you alluded to, Rob, was NASA's landing live stream beginning at 11:15. So we will see you all there. Thank you so much, everyone. And thank you, Rob.
Thank you. See you tomorrow, everybody.